Dr. Brandt is an associate professor in the College of Natural Science at Michigan State University. Her paleontological research interests center on fossil arthropods, their evolution, extinction, paleobiology, paleoecology, and trace fossils. And she's going to be telling us today all about Michigan geology. There's going to be time for questions at the end of her talk. So if you guys have any itching questions for Dr. Brandt as she gives her talk, leave them in either the main chat or there's also a Q&A chat down at the bottom of the screen. You can leave those either place. I'll be checking both of them, and then I'll be moderating that and getting your questions answered at the end of the talk. So leave us some good ones. But with that, I'm going to hand it off to Dr. Brandt.
Okay, great. Thank you, Nick. And I will share my screen. You let me know if it's working. So there we go.
Yes, great.
All right, terrific. Well, welcome everyone. I'm going to get rid of this. So this is the first in a series of Fossil Friday talks leading up to our observance of National Fossil Day. Yes, there is such a thing, and it's brought to you by the National Park Service originally. So to start things off, we're going to have an overview of Michigan's geologic story, which goes back about 2.5 billion years. And for the non-specialists among us, and I am talking primarily to non-specialists, but perhaps even specialists among us can get something out of this. My thesis is every rock tells a story. And if we can read those stories, we can read the history of Michigan that goes back a couple of billion years. So let's get started, because 2.5 billion years of activity is a lot to talk about. So starting with this question, how can we know what happened in Michigan millions and billions of years ago? Were you there? No, we weren't there, but the processes that were acting and the environments that were there left their record in the rocks and fossils. So rocks and fossils tell us about changes in life and environments through time. So we're going to take a trip through time, and like any good trip, we have to do some planning. We should have a map. Our map for the journey looks a little bit different from a highway map. It's very colorful. This is a geology bedrock geology map. The different colors on this map correspond to different geologic time periods. So we've got the map here, and then we have our key to time periods here in this column. And as good geologists, we always put the oldest on the bottom. So these bluish rocks here, which are found in the Western Upper Peninsula, that's our oldest rocks, and we get progressively younger. And like I said, our trip is going to cover about 2 billion years. We're going to start approximately here, and that red arrow indicating MSU, East Lansing, and go up to the Western Upper Peninsula there. Actually, we're going to start up in the oldest rocks and come down to the youngest rocks. We're going to do our trip chronologically. It's about 400 miles, and like I say, about 2 billion years in time. So we will start with the oldest and build our story in chronological order. So we go to the Western Upper Peninsula and to the town of Marquette. Marquette, which is a charming little city and which has a variety of rock types. We're only going to talk about one. There's so much we could talk about the Marquette area. What do the rocks and fossils of the Marquette area tell us about Michigan's geologic history? Well, there's a very particular kind of rock that you can see in Marquette. We are looking down at our feet. We're standing on top of an outcrop that's of this dark, blobby looking rock. There is a notebook and a pencil for scale. And this is a very distinctive rock type. You can see these blobs. I've outlined a few. The rock type is basalt. Basalt is a rock that we can see forming today in places like Hawaii. It forms through volcanic eruptions. And these blobs are given the name pillows. Yeah, right, geologists, right? You know, pillows. that describes their shape, not their hardness. So these are called paleobasalts. They are forming today in certain environments, and so we can use the present as a key to the past to interpret how these rocks form, how these paleobasalts form. So if we were to take a submersible ride in the modern ocean, like off the coast of Hawaii, down to the seafloor, we could see very young paleobasalts. Again, I outline a pillow here. So this picture of the modern seafloor gives us an idea of what Michigan's Upper Peninsula looked like 2.5 billion years ago. So it was very different from today. It was the bottom of a seafloor, and there were volcanoes burping out these pillows of basalt. Now there's a very important difference between our modern analogy and Michigan's Upper Peninsula 2.5 billion years ago. And that is these guys here, these brittle stars, ophiuroids, they would not have been around in those Michigan seas 2.5 billion years ago. Multicellular animals did not appear for considerable time after that. So Michigan's earliest story, or our earliest history, we could say Michigan was born of fire. Fire as a result of volcanic activity. Okay, so how and why were there volcanoes in the Upper Peninsula? To fully explain that, take Geology 201. Dr. Seth Jacobson is teaching that this semester. The answer comes from plate tectonics, our theory, our overarching theory that the Earth's crust, the outermost brittle, cooler crust, is broken up into large segments we call plates, and those plates are moving around due to activity. Molten material, convection cells in the mantle. And Dr. Alan McNamara of our department can tell you more about that. It's his specialty. So Michigan, the Marquette area 2.5 billion years ago was this seafloor where there was plate collision going on. And the result of that plate collision was the formation of volcanoes. These 3 circles show 3 different kinds of settings where plate collisions, or excuse me, there's a plate collision on the left and a plate collision on the right, but we also get basalt forming where plates are pulling apart. So Marquette, the Upper Peninsula, 2.5 billion years ago, very different place than today. We've got, obviously, are there volcanoes in the Upper Peninsula today? No, and it's been a very long time since the tectonic engine that formed those paleobasalts that we see at Marquette. It's been a very long time that that tectonic engine turned off. And you can ask Dr. McNamara why that turned off. So now we're going to get back in our vehicle and go to what I call the striped parts of the map, where you see the colors are basically in swaths or stripes. 3 different stripes in the Upper Peninsula and then in the Lower Peninsula. I've marked with stars along our key here the different geologic periods that encompasses. So that's pretty much the middle part of this column, from the Cambrian to the Mississippian periods. And what do we see when we look at outcrops of these areas, the striped parts of the map? Here we are, a very enthusiastic group of geology students, and let me back up. This outcrop is on the Stonington Peninsula in this area of green on our map, and if we look to our key, we see that corresponds with rocks from the Ordovician period. And these geology students, whoops, have their noses in the rock because they're looking for fossils. These are very fossiliferous rocks. And the kinds of fossils we find in these rocks are the remains of animals that once lived in the sea. One of those is our state stone. And if you're from Michigan, you know what we call the stone. It's the Petoskey Stone. What does our state stone tell us about Michigan's geologic history? Well, first of all, it's not just a stone, right? It's a fossil. And I'm going to ask, you can use the chat function to chime in, and Nick is monitoring the chat. It's a fossil what? Does anyone know what organism the Petoskey Stone started out their life as? And Nick, let me know when we have a response.
The responses are absolutely flooding in from people. Everybody so far is saying coral with a question mark. Oh, now there's coral with a question mark. Yeah, but we're getting coral, fossilized.
Coral with an exclamation mark. Yeah, fossil coral. Now, most of us, thank you, Nick, are familiar with Petoskey stones that have been polished, because that's what we do, right? We find a Petoskey stone and we polish it. Or you find one on the beach and it's already been naturally polished. In fact, this one on the right, I haven't touched it. It was just naturally polished on the beach. So a lot of people aren't familiar with what a raw Petoskey stone looks like, and that's shown on the left. Each of these hexagonal chambers was the apartment, think of it as an apartment complex for a polyp, for a coral polyp. So yeah, our Petoskey stone, it's not just a stone, it's a fossil, and it's a fossil coral, right? Very good. And where do corals live today? Not in the middle of Michigan, not even in Lake Michigan. Corals live in marine waters, and they are especially abundant in tropical marine waters. So here's a picture of a modern marine environment. A picture laying on a tropical beach and offshore. There are corals and all sorts of other animals living in this desirable environment. Here is a diorama, a reconstruction of what Michigan's seafloor may have looked like back in the Paleozoic, back when it was covered by a shallow tropical sea. There are animals that look familiar, like clams here in the foreground, even corals that we've got modern corals that resemble some of these fossil corals. This guy in the foreground is a relative, it's a cephalopod, it's a relative of modern squids. They got very large in the Paleozoic. This guy over here, it's a trilobite. They've been extinct for a very long time, but they're an arthropod, and they have distant relations that are still around today. So here's Michigan during the time it was covered by a shallow tropical sea. A lot different from what we see around us today, right? This kind of vertiginous view of this map, this is a map showing North America during one slice of time when, during the Paleozoic, when Michigan was covered by a shallow sea. The states are outlined in this map just for geographic reference. And if you turn your head, and good old Michigan with our mitten shape, there we are. The light blue represents shallow sea, that we're covered with the shallow sea. The brown is exposed land, and the deep blue corresponds with deep ocean environments. So yes, Michigan's covered by a shallow sea. All of North America looks quite a bit different. It's tilted, right? Since Michigan was covered by a shallow sea, North America has kind of rotated counterclockwise to its present position. It's also, a lot of other things have happened, like South America has joined up. The other thing to notice about what's called a paleogeographic map is the location of the equator is shown by this line. There's a north arrow. And notable is that we are south. We're actually south of the equator in a tropical, at tropical latitudes. So quite a bit can happen in a couple of 100 million years geographically. So, obvious question, are we still covered by a shallow tropical sea? Answer is flooding in, no, of course not, of course not. So sometime after those seas covered Michigan, they drained away. And to see what happened next, we go to the rocks of just down the road in Grand Ledge. They correspond to the Pennsylvanian period. And here we are at Oak Park in Grand Ledge. That's where the climbing ledges are. And here's a very happy geology class out on their field trip. Happy that it wasn't snowing or raining on them that day. If we go across the Grand River to Fitzgerald Park, there's a very well-known outcrop. Every geology student in the Lower Peninsula visits this outcrop because it's so cool, it's so different, it's so unique. You know, there's the sandstone cliffs. You know, they're nice, but they're kind of monotonous, right? Here is this outcrop, and these students are very happy because it's a beautiful day, and they get to be here, and they get to see this. Let's take question or answers on the chat. What do you think that black rock is? Nick.
Looks like we've got a couple of answers, and both people are saying coal.
Okay, yeah, coal, great. Now, stay tuned. What kind of environment does coal form in? You know, a lot of people don't know the answer to that, but I see some of our participants should know the answer to that. What kind of environment does coal form in?
I've got one answer that I know is correct. I'm curious if anybody else can respond with their answer real quick. Ooh, okay. So somebody says high pressure environments.
Oh.
Is, I'm pretty sure, correct. But a lot of other people are saying marshy and swampy.
Nick, keep the editorializing to yourself. Marshy and swampy, yes. Yes, it tells us, yeah, coal forms. Well, let's see. Let's put this puzzle together. Let's use some fossils that, if you were really lucky, you might find at Grand Ledge. A fossil like that, a fossil like that, a fossil like that. All these come together to put together a plant. So we've got fossils from the bark, we've got fossils from the root system, and then we have fossils. Our students can still find these out there. These black stringers are like root hairs coming off of the root. You put all those fossils together, you can reconstruct some of these plants that were growing in this swampy, marshy place, a coal swamp. So coal forms in a coal swamp. Now the pressure stuff comes in later. I mean, there's compaction, but extreme pressure, that's what happens if we took Grand Ledge, if we took Michigan and then squished it, if we started up plate tectonics and let's see, if Ontario and Wisconsin were plates and they slammed into Michigan and metamorphosed our coal, then we would get the hard coal, the anthracite that we see like in Pennsylvania, in the Appalachians, because the Appalachians were a sedimentary coal swamp before they plate tectonics squeezed them and made anthracite. Okay, that was kind of a diversion. Yeah, so the plants, the fossils and coal from Grand Ledge tell us that this area was a coal swamp. Here's a diorama, a very famous diorama. I think that was originally from the Field Museum. We have similar dioramas at the MSU Museum someday maybe we can go back and look at them. But here's what a coal swamp may have looked like. It's familiar, yeah, because we have swampy environments today. Michigan is still pretty swampy, but if we look closely and you know your different kinds of plants, you recognize that these are very strange tree ferns that aren't around today. But yeah, Michigan covered by swamps. Our last stop on our trip, we're going to need a different map because we've kind of run out, we've run out of rocks to look at. This pink shown here at the top and shown here on the map, it's actually not exposed anywhere. So I've been showing you outcrops from these other localities. So we don't have any outcrops of that. So our last stop is going to be in the what we call surficial sediments, the loose sand and gravel, the soil, all the loose material that covers the solid bedrock. So I'm very proud of this animation. Oh, shoot, this animation there. That shows the relative, the relationship between the surficial geology map and the bedrock geology map. The surficial geology is all the sediments, the loose sediments that cover up and obscure our bedrock. So you can see that surficial deposits cover all of Michigan. So we could go just about anywhere in Michigan to look for evidence of what happened during this last slice of time using our surficial geology map. I want to show you a few features of our surficial geology that are close to home. What do Michigan's surficial sediments tell us about Michigan's geologic history? Here's an oblique view of a portion of campus. There's Spartan Stadium, there's Breslin Center, there's the ice arena, and behind the ice arena, there is a hill, just a little kind of isolated hill, and it's covered in pine trees. And a few years ago, one of our geography faculty got permission to dig into that little hill and prove that it is a sand dune. And then they did age dating and showed that it's a sand dune from the last glaciation. And there's Dr. Alan Arbogast looking very pleased with himself because he got permission to dig into that dune. Don't try this at home. Don't take a shovel to places on campus. They probably won't appreciate it. Yeah, so there's an ice age sand dune in the middle of MSU's campus. We also have our rock, the rock, which is another clue to Michigan's glacial past. Where did the rock come from? Well, it's kind of hard to tell now because it's kind of hard to tell what kind of rock is under 15 inches of paint, but apparently it's a very beautiful rock made out of quartz pebbles with these bright red quartz pebbles that we call jasper. And we call this stone pudding stone. It's a reference to British pudding that have red plums, purple plums in the pudding. It's basically a metamorphosed conglomerate. It's not from around here. We have no outcrops of pudding stone in certainly the lower peninsula, but there are outcrops of this rock in Ontario. So how does this rock from Ontario get to campus? Well, thank you, glaciers from the last glaciation. So now, imagine what all these, oh, by the way, we refer to these large rocks that were transported and deposited by glaciers. We call them glacial erratics. They're erratic. They don't belong from here. They came from somewhere else. So our rock on campus is a glacial erratic. How did it get here? It got here transported by an ice sheet that covered Michigan thousands of years ago, from about 19,000 to 10,000 years ago. So imagine here a modern picture, but imagine that's Michigan 14,000 years ago, covered with a sheet of ice. And when the ice retreated, it left behind things like the erratic and the sand dunes. This map shows the extent of that last ice age, the Pleistocene ice age in North America. So we're looking at, here's North America, there's Hudson Bay, there's Alaska. Michigan, there's the mitten. Now the Great Lakes are shown in outline, but they weren't there yet. Those are shown just for geographic reference. The lakes were actually carved out by repeated advances of the glaciers. So pre-last ice age, there were no Great Lakes, there was no mitten. The glacial center, that is where most of the ice was concentrated. There was one here near Hudson Bay. There's another one here in eastern Canada. And during the glacial periods, ice moved out in all directions from those glacial centers and picked up rocks, and the rocks at the base of the glacier served to carve out the less resistant rocks, leaving behind our Great Lakes basins. The other thing I just want to point out is that this last glaciation, most recent glaciation, got about as far south as the Ohio River, and then out west covering Wisconsin and Iowa and so on. So yeah, so that's what North America looked like during the last ice age. Now we're focusing in on Michigan. Maybe you can make out the mitten. The light color covering it represents glacial ice. And you see this finger of ice, we call it the Lake Michigan lobe. Guess why? It carved out Lake Michigan. Here's the Huron-Erie lobe. So yeah, our Great Lakes are geologically very young. They're only about 19,000 years old. Geologically, that's young. Okay, let's advance. I want to tell one more story about our glacial history. And this is geologically yesterday, 6,000 years ago. What's shown on this map, the light blue is water. There's no ice in, well, maybe that's ice. I can't tell. There's water. The N stands for the name of the glacial lake. It's called Glacial Lake Nipissing. And I've got circled here the straits, and that little blob there, that's Mackinac Island. So notice that 6,000 years ago, this glacial lake was very high and Mackinac Island was basically underwater. How do we know that? Well, let's go to Mackinac Island and go to one of the most popular lookouts on Mackinac Island. You're on top of the island and you follow the path to Arch Rock, and then you look at this nice arch and you can look through the archway down to lake level, which is considerably below your feet, and at the road that goes around Mackinac Island. Yeah, Arch Rock. How did Arch Rock get there? It's well above modern lake levels. What's it doing there? Well, we look to modern analogs for how the arch formed, and here is a picture of a modern coastal environment where the rock has been eroded. This arch has been formed. They're called what? They're called like sea stack or sea arch. So we can infer that arch rock was formed through wave erosion at a time when lake level was much higher than it was today. So there's our evidence, one of our lines of evidence for a glacial lake and the height that that glacial lake achieved. Well, I'd like to wrap up with one more story, and that's, what does our state fossil tell us about Michigan's geologic history? Even though the Petoskey Stone is our state stone and it's a fossil, it is not our state fossil. About 20 years ago, some class of third graders decided we needed a state fossil, and so they successfully campaigned to make these fossil elephants our state fossil. Now, there are a couple of kinds of fossil elephants, right? There are mammoths and mastodons. Our state fossil is this guy, a mastodon. And there's a lot of confusion. How do you tell these fossil elephants apart? Well, the best way, the most reliable way, I mean, there are differences in their tusks and this and that and the other thing, but I've always found it easiest to just look at their teeth. Look at their teeth, because they're actually very different animals. They ate different things, and that's reflected in their teeth. So here's a mastodon, an artist's rendition of a mastodon, and here's a picture of a mastodon molar. The brown is the root. Yow, that's a lot of root. And the white lumpy stuff are the bumps, are the cusps that we have on our molars. So, and I don't know if you can see this very well. I've got a resin reproduction of a Mastodon molar, and just for reference, it's like the size of my head, a single tooth. So this kind of tooth with all the bumps, with all the cusps, and it had another one above, one in the lower jaw and one in the upper jaw. And when they came together, the cusps from the one fit in the grooves on the other, and you get kind of a scissor, a scissoring motion. And that kind of motion is good for slicing, and slicing works best on softer vegetation like leaves and twigs. So from the Mastodon teeth, we can infer that they lived in basically a woodland habitat with lots of browse, or another word for browse for that kind of vegetation is mast. So there you go. There's Mastodon, where the word comes from. The other elephants, and we do find some of these in Michigan, but not nearly as many, have a very different kind of tooth shown here on the left. And again, I have a resin reproduction. That's a lot of root, that's huge. And again, it's the size of my head, a single molar. But it's very different from the Mastodon tooth. It has a flat surface, which is really good for grinding. And what do you have to grind? You grind up tough stuff. And maybe surprisingly, some of the toughest vegetation is grass. Grass is tough. Grass has little needles of the mineral quartz in it. They're called phytoliths. And quartz has a hardness of 7. And if you made a habit of chewing on grass, your dentist would say, what are you doing to your teeth? You know, it's a very hard material to chew on. So the mammoths have a tooth that's adapted to grinding grass. Mastodons have a tooth that's good for slicing up softer vegetation. In Michigan, we have many more mammoth fossils than Mastodon. And from that observation, we can infer that the environment of Michigan during those times when the ice sheets melted away looked more like this picture of a woodland habitat and not so much open grassy areas. The reverse would be true. Here's a little aside. If we were to go to Nebraska, Nebraska has many more fossil mammoths than mastodons, reflecting the fact that Pleistocene Nebraska was a lot like modern Nebraska, a very open grassland environment. And we can tell that from our fossil elephants and from looking at their teeth, the power of teeth and bones. So let's summarize and wrap up. We'll use this colorful Ray Troll art showing the geologic timescale as our framework to summarize what we talked about. The oldest rocks in Michigan are evidence that there was active plate tectonics. There were volcanoes in Michigan. How cool is that? Those pillow basalts. Then obviously tectonic activity stopped a long time ago. We have no volcanoes today. What we see next are all these sediments, limestones, shales, sandstones that were deposited in the shallow seas during most of the Paleozoic era. Those seas drained away, and then we see the coal swamp of Grand Ledge, so nicely preserved in Grand Ledge. And then we see these surficial deposits, the erratics and the sand dunes and the erosional features carved out by glaciers. There's our story. Oh, wait a minute. There seems to be something missing, like right there, like the whole Mesozoic and a lot of the Cenozoic. What's going on in Michigan there? What are the fossils from the? I mean, this is the time of the dinosaurs, right? Where are the dinosaurs? Where are the dinosaurs? Well, unfortunately, they're not in Michigan, and this is why. What do Michigan's rocks and fossils tell us about Michigan's geologic history during the time of the dinosaurs? It tells us there were no dinosaurs. What do we find? Fossil pollen! Yay! How exciting! No, it really is exciting. It's not dinosaurs. But pollen, like teeth, can tell us a lot. Pollen, what kind of plant did it come from? Palynologists can do that. We have a palynologist here at MSU. She's in the geography department, Dr. Catherine Jansa. You can tell a lot about environment from looking at its fossil pollen. And what the fossil pollen tells us is that Michigan, during most of the Mesozoic, probably looked like this. This is a photo showing modern day Badlands from South Dakota. Very dry, very arid. So there's not a lot of vegetation. So there's not a lot of animals living there. And also, there's no shallow sea, there's no coal swamp, which are really good environments for animals to live in or near and die and get buried and preserved. So maybe some dinosaurs walked across Michigan and died, but their bones were laying there and they decomposed and they're not preserved. So unfortunately, nope, none of these in Michigan, except in our wonderful museums. So just to summarize and wrap up, and then we'll take your questions. Michigan's geologic history is written literally in the rocks and fossils that are under our feet, literally under our feet. And it's a story of processes in order of fire and water and ice. Pretty much covers everything, doesn't it? So thank you for coming. I'll try to answer any questions you have. And as Nick said, go to the museum website to find out about all the other events that we've got planned for our virtual celebration of National Fossil Day. Okay, Nick, questions?
Yeah, so we have a bunch of great questions. So I will go through a couple of them. The first one actually got via email before the chat started. So this is from Madeline, age 7, and she was wondering what the most common rocks are in Michigan, and if she found a rock in her backyard, what it might be.
Okay, well, that's easy for me to answer because I had my class that I'm teaching this semester. Their assignment was to go outside and find a rock and take a picture. And the most common rock is probably going to be a little pebble of granite or an igneous rock that was carved out of rocks from Canada and transported in a glacier and then deposited during the Ice Age. And granite is so common because it's tough and it could withstand being eroded and transported and deposited in Michigan. And so many of the rocks that we looked at for our class are basically granite or some igneous rock. Now, if your question were what's the most common fossil, that would be fossil corals. 9 times out of 10, when someone brings us a fossil, it's a coral. It might not be the Petoskey Stone coral, but kind of for a similar reason, corals had this heavily calcified, mineralized, a hard skeleton. So they're tough, right? They're robust. I don't like that word, but they're hearty, and so they could take the erosion, being eroded out of the layers where they were buried, and transport it and then end up in your backyard. So the most common fossils people find are corals, and probably the most common rock, it would be some sort of igneous rock that is imported from Canada. Thanks for the question.
Yeah, no, it's a great question. I actually have found fossil corals in my own backyard just a couple days ago. I found a little teeny tiny, I think it was hexagonaria, similar to that. So yeah, you can totally find them in your backyard. And then we're going just kind of in order of what you talked about in the talk. So when you were talking about those really cool volcanoes in the Upper Peninsula, you said that there was no multicellular life at that point in the UP. Do we have any fossils of single-celled life in the UP?
Oh, yes, we do. And darn it, I didn't put that slide in my presentation. Yes. Stromatolite, cyanobacteria. When I was young, we used to call it blue-green algae. Now it's cyanobacteria. And they form slimy mats that trap and bind sediment, and they form layers, and we call those stromatolites. Yes, and we have a very famous locality, again, near Marquette, where these fossil stromatolites are exposed. In fact, it's such a famous locality, it's in textbooks. So we do have evidence of some of this earliest life in Michigan, right?
And then we had another question about the volcanoes as well. And somebody asked, would there have been big volcanic eruptions from the volcanoes in Michigan?
Okay, so we have to define, what do you mean by big? So just briefly, without giving you a whole seminar on plate tectonics, think about Hawaii and the volcanic eruptions on Hawaii. Now, do we consider those big or are those small? Yeah. There's a situation where we get very explosive, destructive eruptions, and that's where, that's in this right circle, where we get the situation where we have an ocean plate and it's colliding with a continental plate, and that produces a magma that's very sticky, and to erupt, the pressures have to just be really, really huge, and so they erupt explosively and destructively. Mount St. Helens was an example of that. Italy, 4 years ago, there was no, excuse me, that was an earthquake. Earthquakes and volcanoes are different things. So were there big, there was not this situation. And if any geologists are watching who could correct me, please do. It was more like this situation. I mean, yeah, it would have been, I mean, it would have been cool. I mean, right, any level of volcanic eruption is cool, right?
Liquid rock, it's awesome. Yeah.
It's awesome.
So that was a really good one. And then we had 3 more. So one of them asked, when you were showing the diorama of the Field Museum, there was a dragonfly in the background, and it wasn't really a question, but it just said, "That's a big bug." So could you talk
Yeah.
about insects during that period?
Yeah, big dragonflies. I mean, there were huge dragonflies, and there are various ideas out there about why were there such big dragonflies, and some arguments center on the composition of the atmosphere, being more oxygen in the atmosphere at that time. But other things are big, like that's a roach, by the way, on that tree. Yeah. So, I mean, there was a variety of sizes of animals. Oh, but there were also, you don't see it in this diorama, there were like these millipede like animals that were a couple of meters long too. So conditions were, let's just say they were just right for supporting a diversity of insect life forms. They were apparently very, very happy in the environmental conditions of these ancient coal swamps. Yeah, lots of bugs.
Yeah. And then we had one more question when you're talking about glaciers. Then you're talking about the Lake Michigan lobe. And so it said, why did the Lake Michigan lobe form a lake, but the Saginaw lobe did not?
Oh, but it did. It did. We've got Saginaw Bay.
Oh.
Why is that happening? Why are the lakes where they are? We have to go back to our roadmap. So if you take a look, okay, where the lakes are, we don't plot the geology. It's like the geology doesn't exist. Well, of course, there's rocks at the bottom of the lake. And the reason the lakes are where they are, the kind of rock, the bedrock that was there was less resistant to erosion. Like, think about shale as being something that could be easily eroded versus solid limestone or a solid sandstone. So the lakes formed along pre-existing, sorry, I was going to get technical, pre-existing drainages that before there were glaciers, there was like a river that ran like here and like here. And where do rivers form? They form where they can erode and seek this lower level, right? So rivers are forming where there is less resistant rock type. And then when the ice advanced. It was following the pre-existing topography. So we're getting a hint of what pre-glacial drainage, I'm sorry, I think I'm more technical, what pre-glacial drainage in Michigan was like. Yeah, the lakes are where they are because there was softer rock, or it was fractured, it was easier to erode. And so for whatever reason, maybe the Saginaw lobe just wasn't as thick. I don't know, now I'm getting out of my realm. Or it ran into more resistant rock type, like it runs into the Pennsylvanian. We don't see that eroded here, right? But where Lake Michigan is and Lake Huron, those are limestones and shales that were less resistant and could more easily be eroded. That's this non-glacial geologist explanation for you.
But so what I'm hearing then is at least the Saginaw lobe probably helped form the shape of Michigan, right? It helped.
Oh yes, that's Saginaw Bay. Yeah, that's our thumb. We wouldn't be the mitten without the thumb, without the Saginaw lobe, right?
That's so cool. And then the last question was about mastodons, our state fossils. And so you had said that we find mastodon fossils in Michigan more often than we find mammoths. But this person just wanted to know, how often do we find mastodon fossils in Michigan?
Every time a farmer drains a low spot in their field, and I happen, I think, to have an extra slide here. Just a couple of years ago, okay, 5 years ago already, a team from the University of Michigan was called in to this farm in Lima Township, or is it Lima? But actually, this was a mammoth. This was really interesting because the most recent find that I'm aware of, this 2015 find, was a mammoth. So that was a big deal because mastodons are more common. And it is, I mean, the modern Michigan, what our topography, our landscape today isn't that much different from Ice Age Michigan. Where there are low swampy areas today, those were probably low swampy areas 10,000 years ago. And those are good places to look for some of these Pleistocene animals, because those would have been places they fell in and died, they would get buried and more likely preserved, like this guy here near Chelsea.
That's so interesting. I knew a lot about the mastodons. There's a picture that goes around the internet that you guys might have seen. That's I think it's a backhoe that's lifting a mastodon skull out of a field, and it seems like it cycles once every couple of months. I always see it pop up different places, but I didn't actually know about the fact that it was a mammoth found in 2015. That's super interesting. Yeah, so that's the end of our questions. Unless anybody has any else that they want to send in really quick, I think we can kind of wrap up. But thank you so much. Sorry, do you have something to say?
Sure.
Yeah.
Nick, did you want to put a plug in for our fossil ID thing?
Oh, for sure. Yes. So we are part of the National Fossil Day event. We're also running a fossil ID. So usually at National Fossil Day, people can bring in fossils and have them identified by paleontologists. Unfortunately, we're not doing a in-person event, so we can't have people bring in fossils, but you can email images of your fossils to an email that we have set up called msumfossilid@gmail.com. And you can also find that on the MSU Museum website. If you go to the National Fossil Day tab, it's listed right there. And so if you have any fossils at home, you don't know what they are, or if you want to try and stump a paleontologist and you think you do know, not that you can stump a paleontologist, that's what they do. But if you take a picture of it with a ruler, like Danita had that picture of the pencil in the notebook for scale, just so the paleontologist can know how big your fossil is, and try and take some pictures from multiple angles, you can email that to us, and then we will have it identified probably as part of another live stream, and we're still figuring out whether that will be scheduled ahead of time or if that will happen on the actual day of National Fossil Day. But regardless, keep an eye on our social media and our website, and you'll be able to see when your fossils can be ID'd. We've already got some cool ones coming in, so it should be pretty good. I don't see any other questions, so I think we can wrap up there. But thank you so much, Dr. Brandt, for coming out and talking to us about Michigan geology. I know I learned a whole bunch, and I'm an educator at the museum, so it's always good to learn more about your own state and the ground underneath your feet.
Yeah, exactly. Well, thank everyone for taking the time to come today. We really appreciate it and hope to see you at some of our future events too.
Yeah, for sure. And we'll be sending up a follow-up email, or sending out a follow-up email with links to all the future events, so you guys can sign up for those as well. But thank you guys so much for everybody for tuning in.
Okay.
All
Bye.
right. Bye.